or that may or may not be important in the dynamics of H2 regions. And so just to kind of go on, a lot of the stuff that I work on focuses on how does stellar feedback, so the injection of energy momentum by young stars, mostly massive stars, affect the dynamics and the formation of massive stars and star clusters and the gas and the dynamics of the gas that surrounds them. And so my favorite example to show is 30 Doradus in the LMC. It's our, it's our closest example to a starburst star cluster, or like a superstar cluster in the local universe. And the nice thing is when you take a composite image of 30 Doradus, like shown here, you can see how the different modes of feedback actually affect the gas that surrounds these young clusters. And so here, this is a composite image showing, outlined in blue. You see this is X-ray emission from the hot diffuse gas that is created by the shock heating of stellar winds from these massive stars. This is R136, which is a very massive star cluster that you can see is blowing gas out. And so the X-ray emission traces how this gas can actually blow bubbles in the surrounding H2 region. You also have effects from stellar radiation. So here in the green, this kind of shows the first absorption of the radiation field. And dust is a primary absorber, and so you get this dust remitted reprocessed radiation pressure enhanced. So basically, this kind of shows the effect that both radiation, including also photonization, and winds can actually have a very destructive effect on the surrounding gas. And one of the interesting things with stellar feedback is that it can actually disrupt clouds, molecular clouds out of which these stars form. So this is NGC 3603. Sorry, this is not my pointer. I'm going to use to it. This is NGC 3603 in the Milky Way, where you see this compact star cluster, and then you have this gas that was likely ejected from the stellar feedback processes. And furthermore, if you look at GMCs that are forming stars, you find that the star formation efficiency per freefall time is actually quite low, and this is probably attributed to stellar feedback. And also, if you can eject a lot of gas from these star clusters or from these GMCs as the star cluster is forming, you can actually lead the cluster unbound and causing the clusters to dissolve with time in a short amount of time. And so to understand how the different components of feedback actually couple to the ISM is very important in understanding how long these star clusters can survive and how the gas can be pushed out. So I'm going to focus on feedback from stellar winds today. And so you can think of, so this is R136. It's a massive star cluster in the LMC in 30 Doradus. And you have a lot of massive stars that are densely packed. And these stars are going to give off fast stellar winds that can then collide with the winds of nearby stars. And then you can shock heat the gas to millions of degrees Kelvin. And that hot gas will adiabatically expand and fill the H2 region. And we can see this because this gas is millions of degrees Kelvin. We can see it as this diffuse X-ray emission. Like, so if you look at the soft X-ray emission, so 0.5 to 0.2 keV, for example, with Chandra. And this has been seen in numerous star clusters. So this is just a handful. This is something that came out recently where you see these hot bubbles within these H2 regions. And so this hot gas can push on the surrounding gas and potentially affect the star formation process and also eject gas from these clusters. Now, a lot of galaxy formation people like to look at supernovae as a dominant feedback process, and it turns out if you compare the energy injected by stellar winds over a star's lifetime, it's actually comparable to the energy injected by its resulting supernovae. So if you think supernovae are important, then you would hope to think too that if you just kind of do an accounting exercise, that energy momentum injection by wind should also be important during the cluster formation process or the H2 region lifetime. But this is work done by Laura Lopez, where she looked at 30 Doradus, and she mapped the different pressures associated with different feedback components. So the direct radiation pressure, which falls off as 1 over r squared. Also looking at the dust emission, you can get the dust reprocessed radiation pressure, looking at the warm gas, the H2 radiation pressure, and then comparing the X-rays, you can get the hot gas radiation pressure. And it turns out that you see that the pressure associated with the hot gas is a lot weaker than these other components. And then also, if you look at the energy content within the hot gas, so from the X-ray emission, you can constrain what the properties of the hot gas is. And then if you look at the stars and estimate what the total energy injection rate is, you'll find that the energy that you would expect to be within the bubble is much larger than what you actually see from the X-ray emission. And so this suggests that that the hot gas is leaking out of the H2 region, and the question is, well, how? Like, where is this energy going? So this work kind of looking at different ways you can lose the energy or transfer the energy via other processes. And so I'm just going to go over our model and how we apply this to certain H2 regions in the LMC and the Milky Way. And then I'll just go over the different energy mechanisms that we consider where you can transfer the energy, and then talk about the results and how it kind of affects our understanding of the dynamical importance of stellar winds in H2 regions. Okay. So our model is pretty simplified. Imagine you have a stellar cluster in the center of an H2 region or a molecular cloud, and you have many stars, and these stars give off winds, and those winds will collide with nearby winds and shock heat, and you get this shock heated gas that expands and fills the bubble. And so the first thing is we want to know what the total energy is given by these stars, by winds. And so we need to know what are the spectral properties of the stars within the H2 regions and what the total wind energy is, the DEDT. And then we want to be able to characterize the hot gas, the shock-heated gas that you can see with X-ray observations. And so we also require X-ray observations to be able to constrain what the number density and the temperature of the gas can be. And then finally, because we want to know what is the dynamical importance in the H2 region, so how does the hot gas push on the H2 region cell, we require radio observations to determine the H2 region radius and also the expansion rate. And so this allowed us to look at 4 different H2 regions. So 30 Doradus in the LMC, and then these 3, Carina, M17, and NGC 3603 in the Milky Way. Okay. So then we considered several different ways that you can actually lose energy from the hot gas. And so what this plot shows here, what this plot shows here is what is the allowed number density I have as a function of temperature if all of the wind energy was lost via this one mechanism. And so this line here shows, for example, what the number density would have to be for all the wind energy to be lost, for example, by cooling, so radiative cooling of the hot gas. So you can't be above the line because you would radiate more energy than you're putting in, but you can be anywhere below here. And so the white region is our allowed region. So first we took into account cooling, which at high temperatures is really ineffective, but then we also took into account mechanical work on the shell. So how is the hot gas is pushing on the shell. And you see that at low temperatures it's unimportant, but at high temperatures it becomes more efficient at transferring the energy than radiation. We also took into account thermal conduction, so laminar thermal conduction, the typical Spitzer analysis, where this is highly dependent on temperature, which is why you see this large spike, and this can actually be quite efficient at removing the energy. Now, this is a conservative estimate because the effect of magnetic fields will actually affect this. So, for example, you can highly suppress conduction if there are magnetic fields between the hot and cold interface, which there likely is for H2 regions. We also took into account the saturated regime because we consider very high temperatures, and this is just saying that the heat flux can become saturated because you can't transfer energy faster than the electrons can move, for example. And then finally, we also considered collisional heating on dust grains. So you can think that at the hot-cold interface, you can mix in dust into the hot gas, and that gas will be sputtered. That dust will be sputtered by the hot gas, transferring energy. And before the dust is sputtered away, you can transfer a lot of energy that way. And we can see here that, based on the taking typical ISM numbers, that this can also be quite efficient at removing energy. So considering these different mechanisms gives us this narrow region of where the hot gas can be for considering what the allowed number density temperature plane is. Now, from the X-ray emission, we can actually constrain what the number density is. So taking the emissivity of the hot gas as a function of temperature, we can take the observed luminosity and infer what the number density is as a function of temperature. And that's what I'm showing here. And so this just shows what the number densities are as a function of temperature for the different H2 regions. And then we can overlay that on the plot here. So basically, we have to lie somewhere on here to be able to explain where the energy is. Now, since we can constrain the number density, then we're no longer have to have this 2D plane. We can just constrain our analysis to the allowed number density from the X-ray emission. This is the same plot for the 4 H2 regions. The stars here just kind of denote the spectral temperature inferred from the X-ray emission observed in these clusters. So this figure here just shows what the energy output or energy transfer rate for each energy sink mechanism as a function of temperature. And you can, like I said before, you can see at low temperatures, cooling is very efficient, but at high temperatures, very inefficient. And then, of course, conduction becomes super efficient at high temperatures. And then we kind of do a simple accounting exercise, which is just to add up these contributions. And we can see here, even considering along these certain temperatures, we could still be missing some of the energy. But what we find is under our most conservative estimates, we can actually account for all the energy in 30 Doradus and M17. But we're still missing energy in Carina and NGC 3603. And so just to give you an idea, so these stars, like I said before, are the temperatures inferred from the X-ray observations. You can, and this just shows the table of the different contributions for these temperatures. So barely less than 1% of the energy goes into cooling. Mechanical work is actually quite unimportant for Carina NGC 3603, a little bit more important for 30 Doradus, and about 40% of it goes into the pushing on the shell around H2 region shell around M17. And that's an interesting case because M17 is the youngest H2 region that we consider is about 1 mega year old. Whereas these are older, so this might suggest that maybe early on feedback from winds is important. And these are just upper estimates, but you see like under our most conservative estimates for conduction and dust, you can lose a significant amount of energy or transfer a significant amount of energy through those mechanisms. Okay. So where's the missing energy? So kind of showed you along this analysis, there's many different ways you can lose it, but we did have a lot of simple assumptions. So the first one is, okay, thermal conduction. Under our conservative estimate, you can basically lose most of the energy that way. However, it turns out that let's say you have a H2 region that's expanding into a magnetized medium, which is likely the case since the ISM is magnetized. What happens is that as the H2 region expands, you actually sweep up magnetic flux into the shell. So even if you started with a tiny magnetic field, the magnetic pressure is going to be amplified in the shell. And then, so that's just going to kill energy transfer through thermal conduction. Another thing is dust heating. And that just depends on also like how quickly you can replenish the dust, because the dust will be eventually destroyed through sputtering. And here you can see this is showing the dust destruction timescale as a fraction of the crossing time. And so for the temperatures considered here, we see that the dust can survive for a few crossing times. So that suggests that dust heating probably helps, but we also need to know better like how much dust can we mix into the hot gas. We just use the typical ISM 1% conservative estimate. And also, how does dust get right into the H2 region? It's likely mixed in. It can also be put into the H2 region through winds from evolved stars and so on. Another thing that has been looked at before is actual physical leakage of the hot gas, and this has been seen in numerical simulations. So here's an example here. where you have, this is a simulation from Rogers and Petard, where you have a molecular cloud, and they put 3 O stars in it. Okay, they put 3 O stars in it with winds, and what they find is that basically the hot gas that's generated kind of seeks the path of least resistance, and so you can because the sound speed of the hot gas is faster than than what would be the expansion rate of the H2 region. It's all greater than 10 kilometers per second for the ionized gas. It can just simply escape outwards, and so what they find is that the hot gas can actually leak out of the low density channels of the turbulent medium. And you can characterize how much leakage is happening. So if you say all the energy is lost through leakage, then that depends on the covering fraction. So how much of this H2 region is kind of covered by a shell. And so with our data, our analysis, we can also kind of estimate what are the upper and lower limits of that. So for example, M17 likely has a large covering fraction, or would require a large covering fraction, so we're just taking into account the mechanical and cooling work. But that it kind of varies, that there's probably a lot more leakage happening in, for example, Carina and NGC 3603 than there is in 30 Doradas and M17. Because we weren't able to account for all the energy in Carina and NGC 3603, we can also put lower limits on this. And so this kind of, including conduction and dust, further constrains the allowed covering fractions for these H2 regions. And then another possibility, which also requires new simulations to do, is instead of laminar conduction like we considered, is actually this other thing called turbulent conduction, and that's just that you have rapid mixing between the hot cold gas at the interface, and basically you develop these instabilities in the shell, and you can mix in cool gas with the hot gas. And the one signature of that would be you're mixing millions of degree Kelvin gas with the photoionized gas to 10 to the 4 Kelvin. You would end up with gas that's about 10 to the 5 Kelvin that would radiate right away. And so a signature of that would be to see if there's like an excess of like O6 emission around H2 regions. And that has actually been seen, or it's hinted that has been seen at the Carina Nebula. They saw an excess of O6 emission with fuse several years ago in the direction of Carina. So just to summarize, you can use the X-ray emission from H2 regions to constrain the properties of the hot gas. And then from that, you can estimate where the energy is going. So if you know the total wind energy from the stars, then you can look at other mechanisms such as cooling, mechanical work, conduction, etc., to see where most of the energy is going. And we find that the bulk of the wind energy doesn't go into cooling, radiative cooling, and not even into mechanical work. And so this suggests that feedback from stellar winds, at least for evolved H2 regions, may not be as important. Like it's not fully coupled to the ISM. And then there's several different possibilities of where the energy can go. So thermal conduction or dust heating might help. But likely over laminar thermal conduction, turbulent mixing is probably, turbulent mixing of the hot and cold gas at the interface is probably more important than thermal conduction because these H2 regions are magnetized. And then also physical leakage is a strong possibility. Thank you.
So how do you put in the length scale into the thermal conduction? So if you have to radiative process that's going like something like per centimeter cube per volume.
Yeah.
But the conduction must be like a diffusion equation, so there has to be a length scale in there. So how do you put those on the same plot?
Yeah. Oh, I'm trying to remember how we did that. I believe we say that it's of order. Man, I would have to look at the equation because I know we talk about. I think it's of order the H2 region size. I would have. Let me talk to you afterwards. Okay. I would have to. We talk about that in the paper, and like I said, it was written 4 years ago. But we definitely talk about that, about our estimate for the length scale for thermal conduction. Yeah.
So you said, you talked about the temperature
So that is a highly, so that's another thing. That was a simplification. We assume a filling factor of 1 because we wanted to be very optimistic about the effective feedback. So for example, if the hot gas is clumpy in these H2 regions, then that just means that the hot gas is going to be less dynamically important because if the filling factor is low, then you're not going to have a big surface area for the hot gas to push on. So we were very conservative in saying under the most optimistic scenario where feedback could be important, could we do that? And this is a highly simplified model. Like I plan on following up with actual 3D simulations out of a turbulent cloud with active star formation to actually see what the filling factor of the hot gas is, how does dust mix in the hot gas, and so on. Does the hot gas escape? But this was kind of like an order of magnitude, simple estimate to kind of see how important the hot gas can be dynamically. Oh, sorry. Yeah.
So both with thermal conduction and the turbulent mixing, we expect to get intermediate temperature gas, and that could be radiating strongly in the ultraviolet. But in ultraviolet, you really can't see that. But you could see, for example, carbon-4.
Oh, okay.
In both cases.
Oh, okay.
So I don't know if you.
I haven't thought about that. That'd be interesting because I know there's not, a UV telescope capable of measuring this now, and so that'd be interesting. I have to look in the literature to see if people have looked at C4 emission around these H2 regions. Yeah, thank you. Oh, sorry, you and then you. Sorry, and then you.
A shock set thousands of kilometers per second only puts 50% of the energy into the electrons. So most of the energy actually would be in the ions. And then you have a longer time scale in supernova remnants, but the density is lower. So I just wondered if you look at the cooling equilibration time.
I don't. So we talk a little bit in the paper about if you're out of equilibrium, and it turns out that I think it would change the numbers maybe by a factor or two, or. Like I said, sorry, I meant to reread my paper before, but we have a section where we talk about that, where if it's out of equilibrium, it can lower the density but increase the temperature, or vice versa, and it turns out that it would have a minimal effect in these estimates. So I haven't looked. We just kind of talk about how if you are at an equilibrium, it shouldn't make much of a difference for the number density and or the overall power output. Yeah. Yeah. So because we were estimating, we were talking. Yeah, it could change the temperatures if you're out of equilibrium. But for the energy things that we were considering, at least for work, because that depends both on the number density and the temperature. Because if you're out of equilibrium, that will also affect your estimates for the number density from the emission. And we find, at least for talking about dynamical work in the H2 region, it made little difference.
I was wondering about the implications. So you have these different possible mechanisms for essentially getting rid of this energy.
Yeah.
But each one then feeds energy to its environment in another way.
Yeah.
Thereby potentially influencing the next generation of star formation, for example.
Yeah.
So have people looked at how that comes into play in your model? What some of the implications would be, and perhaps placing constraints based on a whole other set of observations?
Like if you could trigger, if you had rapid cooling of the hot gas, if you could trigger star formation.
Something like
I know
that.
people
I'm
have.
sure there are a whole range of possibilities that I certainly haven't considered. But I think
She's looking into it now. We've been talking about that, yeah. Where, you could, if you had rapid cooling, if you had a thermal instability, you can rapidly cool, get high densities, and maybe trigger star formation. And it's believed, in 30 Doradus, for example, that there have been many episodes of star formation. So, for example, R136, which is, the massive star cluster near the center, is one of the youngest star clusters in 30 Doradus. There's a lot more evolved stars, out in the outskirts, and so that might have been a triggering event. Yeah.
Back to the oxygen 6, there have been a lot of surveys of oxygen 6 with Copernicus, with Fuse, in all sorts of directions. Now, have you taken a look at that? In other words, they must pass through lots of H2 regions because you use the background stars, the OCDs and stuff to do that. Have you beyond 30 Doradus to see if there's anything statistically associated with these H2 regions?
So I looked at the Fuse paper, and they did talk about that they do see an excess of emission in the direction of Carina. And I think because of the resolution.
Emission or absorption?
I'm sorry, absorption. I don't know. Yeah. No, I think emission from Fuse, right?
No.
Yeah, I think it was 06 emission. Yeah, and they see an excess, but they say it's along the direction, so they can't really. I think because of the resolution, they cannot pinpoint it. So we discussed a little bit about the implications of that could be a signature of this turbulent conduction.
Sight lines of 06 all over the place.
Okay. Yeah. Yeah. I think with Fuse, at least, that was the only thing I saw that was related to these H2 regions, where they kind of hint that that emission could be related to Carina. Yeah.
A lot of data out there. Okay.
Yeah. Thank you. Okay.
So can I ask a question related to Rosen's?
Yeah.
If we take gas from this hot state and put it in this intermediate state, can't it still then do work on its surroundings, cause them to adiabatically expand? Or is the point that you're in a portion of the cooling function that's much more efficient?
Yeah, so because
How does that all work out?
So like for example, if you get 10 to the 5 Kelvin gas, you're going to instantly cool. And so since the pressure depends on the temperature, I don't know, I think you'd have to compare if you cooled rapidly what the resulting number density would be and if you're in equilibrium, then it should do the same. But I think that the main idea is that the hot gas is going to expand, is going to move at the sound speed, right? And that just depends on temperature and not density. So you can be more effective with hotter gas than the lower temperature gas.
I see.
Yeah.
Okay, thanks.
So with all this talk about rapid cooling and from thermal conduction or the rapid expansion, in X-rays, that usually translates to ionization state or a little bit not what we usually see.
Okay, yeah.
We don't see them under ionized, instead we see them over ionized. Do you remember by any chance what the state of this of the ionization timescales of this X-ray observation?
So I know in Lisa Townsley's paper, so she has a paper that I referenced that she looks at the X-ray emission from 3 of the H2 regions. I think it was all, maybe not Carina, but the other, or maybe not N17, but the other 3. And so what she does is when she does the spectral fitting, she does fit models to see if it's over ionized, and she finds that she does find better fits if it's over ionized. Yeah. Is that?
Final question as we switch laptops.
Oh, cool. That works.
We can do that.
Yeah.
Let's thank Anna again.
Thank you.
I do not know how that works.
I didn't either.
Shift. What is this?
Oh, it does this. Yeah, you can just get out of it, I think.
Okay.
Because it's not an actual keyboard.
Okay. Wonderful. Yes. So thank you very much for this opportunity and for coming and listening to me. We have heard, this is a fantastic series where we have learned different manifestations of winds, outflows and inflows from different objects in the universe. And so I'm going to talk about radio supernovae, which is another way of looking at how the stellar outflows show up at very late stages in the stellar evolution. So I'll do a very broad brush description of various phenomena within the radio supernovae instead of talking about only one result. So let's see how much can I cover. And I'm afraid that I won't be able to cite everybody's work. There's a lot that has gone, so apologies in advance. Right. So real quick description about supernovae and how things happen. So you have a star which is sitting, massive star which sits there for a million years, and it drives powerful winds which modify the surroundings. And then one day the star explodes. As it explodes, it emits radioactive material around it, and which is extremely bright in optical at about 6,000 kelvins. That's how we discover supernovae. But way ahead of it, there is a powerful shock wave that goes out, and there is a material which is at very high temperature behind the shock wave. It's at about billion kelvins. And there is a little bit of magnetic field which then starts radiating synchrotron emission, which we see as radio supernova. So this is a forward shock that moves out at very, really high speeds, like 10,000 kilometers per second or so. But then there is another shock wave that goes back into the ejector, which is called the reverse shock, into the dense ejector. So it's also at very high temperatures, like 10 million Kelvin, and it emits primarily in X-rays. So this is the basic. But the shock speed, as we have seen in most of the radio supernovae, it's really fast. It moves at a fraction of the speed of light. So it samples the space around the star very rapidly. And if you compare that with the stellar outflow, stellar outflow is about 1,000 kilometers per second, the stellar wind, or in the case of large stars, it's about 10 kilometers per second. So compared to that, the shock speed is about 30 to thousands of times faster, which means you're sampling the space around the star really rapidly. So another way to put that is, if you observe a supernova for about a year, you're actually sampling the space around the star, what happened to the star about 1,000 years before it exploded. So it's a very powerful probe of sampling what happened in the star's life just before it exploded. So that was observations, radio observations connect with the progenitor history very well. And we can use this not only as a probe, but also to see what happened in the star's life, what kind of a star exploded, and even to predict new phenomenon about these events. I very much like to give an analogy of this with the old album. Like as the supernova shock wave propagates through the medium around the star, you're looking into the history of the star, which is like flipping through an old album and seeing what happened in the past. This is how typical observations look like. What is plotted on the left side is the spectrum of a supernova. And you can see that this is a signature of synchrotron self-absorption. And on the right side, of course, the spectrum evolves and you see a light curve. So on the right-hand side, we have shown a light curve at a particular frequency. And again, you can look at what the characteristic rise time and fall times are. That tells you what's happening. So I can, from here, deduce that it's a freely expanding shock wave. It's not decelerated. And using these simple observations, you can estimate some of the most important parameters about the supernova or the star that exploded, which is that the supernova shock is moving at 20% the speed of light. And what is the density around this star? So how this star was losing the mass. It's about 10 to the power minus 4 solar mass per year for this particular case. But then, of course, there are supernovae of different types, and these numbers differ. So here is another observation, supernova 1979C. It's a very old supernova. I don't know how many of us were actually born that year. But they're beautiful observations. It's a light curve at 2 different frequencies, and you see modulations, beautiful modulations at late times. Now, how to produce modulations in density at such late stages in the star's life? So in this particular case, so if we assume that it's a single star exploded, it's very difficult to explain it. But people are smart, and they came up with different explanations. So they thought maybe it's a binary star, and if it is a binary star, it will modify the density profile around it. One of the star will explode, and it will tell you what the density profile looks like. So this is a beautiful modeling or a feasible explanation of this light curve. So observing a radio supernova tells you that this distant star which exploded is actually not a single star, it's a binary star. And I think Morgan appreciates this very easily. I hope you all do that too.
I just love those spirals.
Yes. So that's a brief introduction. So I'll split my talk into 2 aspects with that motivation. One is, what do the radio observations of supernovae tell us about the progenitor properties, what kind of star exploded, and how can we use that to make new predictions about different phenomena or to understand about fundamental physics. I'll try to give a few different examples of different supernovae, and let's see how far can we get. So type 1a supernovae, very famous. We have used them for cosmological expansion and various other things. And the frustrating thing is that we still do not know, is it a single degenerate star exploding or is it the double degenerate star explosion? And let's see how radio observations can help us. So there are two broad models. One is that you have a white dwarf, which is accreting matter from a red giant star, and it crosses the critical mass limit and explodes. That's single degenerate type 1a model. And the double degenerate, where you have two white dwarfs colliding and producing a type 1a explosion. So this is an example of PDF 11 KLY, another type 1a supernova, which happened very close, like few megaparsecs away. And we observed it with radio observations. Sorry, that was too fast. This is a beautiful radio observation of this particular supernova. That's the galaxy you see. And the zoom in shows that where this crosses, that's where the supernova should be seen in radio, but we didn't detect it. The fact that we did not detect it tells us that there must be extremely low density material around this particular star. And we can put very deep limits. So that was one case, but we then observed lots of type 1a supernovae nearer and farther. And none of them were detected. So not one type 1a supernova has been seen in radio, which tells us that the material around these type 1a supernovae, whatever the progenitor is extremely low density. And for example, the shaded regions here show different models. That's the wind model, and this is if you have a constant density medium around it. It tells us that the mass loss rate must be extremely low, 4 into 10 to the power minus 7 solar masses per year, or it should be much lower than 1 particle per centimeter cube. So what kind of stars have such low mass loss rates? Then this shows observations in different frequency bands, and again, the result is null. We don't see anything. But using this, we can estimate what the mass loss rate must be around these systems. And that tells us that these are not white dwarfs. That if you have a white dwarf, you would expect much more denser material. And the result is that the white dwarf red giant star association, which is the single degenerate model, it doesn't work for type 1a, at least from these observations. And we rule out that more than 90% of the type 1a supernovae rule out this association. Now let's move on to another result, which is GRB Supernova Connection. The GRBs have very nice, rich history of how they actually happen, but soon after their first GRB was detected, within a few years it was realized that these are also the explosions of stars, extremely massive stars. And instead of going through different theories, I'll just give you this picture where we know that GRBs and supernovae, these are both explosions of massive stars. But there are certain differences. So supernovae are non-relativistic expansions and they're spherical explosions, whereas GRBs are collimated explosions and relativistic outflows. But then we have discovered a few things which sit in between. We tend to call them engine-driven supernovae. So what's the difference between long GRBs and supernovae? So GRBs are relativistic, finely collimated, and strongly decelerated outflows, and they're detected in gamma rays. Supernovae are non-relativistic, spherical, freely expanding, and they're detected in optical. They're discovered through optical emission. But one extremely important point about GRB supernova association is that every supernova that is associated with the GRB is of a specific type. It's always type 1c broadline, which means it's a compact star which doesn't have hydrogen or helium around it. And it's a massive star. Now, many supernovae have been followed. Many supernovae have type 1c broad lines, specifically to see if there is any connection between GRBs and supernovae. And this is a picture that we have. So what is plotted here is the luminosity, radioluminosity on y-axis, and the time on the x-axis. The red points here are the type 1c broadline supernovae, which are the kinds that are associated with GRBs. And the blue are all other kinds of type 1 supernovae. What you see is that most of these type 1c broadline supernovae, they tend to cluster together up there. They're bright, they're fast moving, except there is one which is sitting here. And there are only 2 of those supernovae which we have seen to be moving very rapidly. Like, we can call them mildly relativistic. But most of the others are just normal supernovae. And the question is why? First of all, why there are not enough type 1c broadline supernovae that we see in radio? And the second is, why only few of them have such rapid velocities, whereas we see GRBs almost every day? This is a collection of different observations that Berger and others have carried out. It's a survey. As soon as it was realized that the supernovae and GRBs are associated, they followed up all the supernovae within the local universe, like within within 50 megaparsec. So GRBs are extremely bright, which are sitting at the top. And supernovae they have low luminosities. The result of these surveys is that they followed lots of supernovae, 33 supernovae, but they detected only 4 of them. Now, you would appreciate that it's extremely difficult to hide radio waves. So if there is a supernova which has happened within that distance, and if you observe it with correct sensitivity at a correct time, you should be able to see it. So why is it that we do not detect almost 88% of these supernovae? There are extremely deep limits on their luminosities, though. So what's going on here? This is a typical range where we should have been able to see these supernovae, but we did not. It does make sense in the light of these new observations, as I'll try to show now. So what is plotted here is the mass loss rate on the y-axis and the shock velocity from these type 1c broadline supernovae on the x-axis. It turns out that they all line up in a single line, which is actually the contour of luminosities. So you have faint supernovae here and high luminosities there. It turns out that all these type 1c broadline supernovae, they line up in a single line, which also means that we tend to pick up brighter, faster supernovae. For example, this is a GRB supernova. It was one of the first association, and you can see that it's moving extremely fast with a gamma of about 3. The point is that if this supernova were moving a little slower, like by a factor of 2, it would be extremely faint, and we wouldn't be seeing it. Similarly, this extremely faint supernova that was seen, it was seen only because it was fast. If it were moving slowly, it would be well below the observation limits, and we wouldn't have detected it. Now, if I put together this scene with the observation, the upper limits that Edo obtained, they line up there. So there are a lot of these supernovae. As I said, it's extremely hard to hide radio waves. So if there are supernovae within that range of detections, they should have been seen, but they did not. So they line up, their contours line up in this mass loss shock velocity range, and which means that they're probably sitting there, but they're way below our sensitivities. So the conclusion here is that there's a large population of these supernovae which are sitting there and waiting to be discovered. The expulsion of stellar envelopes. So we know that there are type 1b, 1c supernovae which do not have hydrogen and helium envelopes. If you do stellar evolution theory and simulations, we find that there's no way we can get rid of this hydrogen envelope. It's extremely difficult. It always stays when the star is about to explode. That's from the theory side, but in observations we see that there are supernovae where there is no hydrogen and helium envelope. So how does that happen? Now here is one interesting object, Supernova 2014c. All the gray points are all other supernovae that we have seen in radio, and this is 14c. So it looked like pretty normal supernova, and then in about 200 days, it suddenly shot up by a factor of 50 to 100. At the same time, what we saw is that the H alpha line emission started to shoot up it became extremely bright. So this is there's a connection between these two observations. And what it says is that the shock wave is interacting with high-density hydrogen material out there at 200 days. Now the question is, where did that material come from? So this is the shock shell interaction, and a brief description about this supernova. So there is a shock shell interaction happening at around 200 days, and we estimated what is the mass of that shell must be. It's about a solar mass hydrogen sitting there. It is sitting at 10 to the power 17 centimeters, so it's pretty close to the star. But you can translate this into how many years before the star exploded. It turns out to be about a few decades to centuries before the star exploded. And then the question is, who ordered that? How did that happen? So how did the star manage to expel its envelope within a century before its explosion? Now that is a range, that is a time range which is extremely difficult to probe through numerical simulations, but observations help us to find out that there are these supernovae where you have this material sitting there. Now, we looked at a few explanations how to do that. We know that there are stars which keep exploding, which throwing out material, such as eta Carinae and luminous blue variables, but they haven't exploded. So I can't say that they will explode within 100 years. I don't know. The other is the pair instability explanation that is there. The problem with this scenario is that you still need tens of solar masses of helium before the star explodes, and which means it's still several thousands of years before so the pair instability happens several thousand years before the star explodes. So that doesn't work for a century. The common envelope evolution, we have Morgan sitting here, he can tell us, and we estimated the time scales that's still few thousand years before the star explodes. So in the process of common envelope evolution, if the envelope has to be ejected, it happens several thousand years before. And so we looked at what exactly happens in the star's life about 100 years ago, what kind of nuclear burning is going on. And we proposed that it's the nuclear burning instabilities which are happening in around that time scale that must be leading to this. It's extremely difficult to do these calculations, but it's a proposal. And so for example, we demonstrate here that how many, on the lower panel, how many supernovae are there which show similar interactions, shock shell interactions on that time scale. And on the top, what is plotted is the look back time and what kind of nuclear burning is happening at that time. So it turns out that when most of these interactions are happening, we are either burning carbon or neon. So this is pretty late stage in the star's life. And the nuclear burning instabilities in neon or carbon burning, that could lead to this kind of explosion.
What does the shaded region mean?
The shaded region takes into account various, our ignorance about various things, like uncertainties in observations. Sometimes you don't have observations carried out at a clear cadence, and you miss various things. So it just means, so you can think of this as the lower limit on this fraction versus upper limit.
Okay.
And the conclusion here is that the massive envelopes may be expelled during nuclear burning instabilities in the late stages. Am I done? How many minutes do I have?
About done. But
Okay.
you have a minute, 2 minutes.
Okay, 2 minutes. I'll show you the final result. So we have understood from these various different manifestations of the stellar winds that they can be used to probe the history of the star and what the progenitor is doing, but we can also use it to predict different phenomena. So for example, the cosmic ray acceleration. And I'll briefly show you. So if you have extremely dense material sitting around the star and the shock wave is accelerating electrons to very high energies, it will also accelerate protons to very high energies. And these protons are then going to decay into different products. So the pions will decay into gamma rays, muons, neutrinos, and the muons will then decay into electrons. So we started with protons and electrons. We ended up with various different particles, including electrons. So we have two populations of electrons now, primary electrons and secondary electrons. And just as the primary electrons will emit synchrotron emission, the secondary should also do that. And we should be able to see that. Now, I'll not go through the details of this calculation, but I'll show you a result. Right, so here. So we did detailed calculation of if you actually have the secondary electrons happening, can we see them? And what is shown here is the red curve is the primary electrons, what the spectrum will look like, the synchronous spectrum from the primary electrons. The blue curve here is the spectrum from secondary electrons, and we evolved it over various time scale. As you can see, at very early times, 2 days to 2 weeks to a few hundred days, the blue curve dominates the red curve, which means the synchrotron emission from secondary electrons is much more dominant than the primary electrons. So if we do observations in the correct time frame and at a correct frequency, we should be able to distinguish this effect. So this is the typical range, which is it's like a sweet spot in frequency as well as time where we should be able to see this. And ALMA is the telescope which operates at these frequencies. So that's our proposal, and if we can see this, it tells us directly that how the cosmic ray acceleration happens in supernovae. So with that, I will stop, and I'll leave you with this slide of conclusions. Thank you. Yes.
Okay, so I would propose that we pause for 2 minutes, get pizza, and then come back for Q&A together.
Okay, sounds good.
Thanks. Thank you.
Okay, all right, so we approximate it as T over R.
I'm happy that I managed to cover most of it.
Yeah. Yeah.
The interacting wave system is amazing.
Sorry.
It is amazing.
It's amazing. And plus, we have data over so long for that.
Yeah.
Supernova, yes. And it also encourages us to observe being in the supernova. See what's
For a long time.
It's unbelievable, otherwise there is no way to know it. There is
I saw, this is probably just incidental, but I saw a title the other week about supernova something that like re-brightens
Yes.
from CSM
That's right.
interaction.
That's right.
So
that
1,000 days afterward or something like that?
Yes, it keeps
Or
happening.
even more? Yeah.
There are ways, so there was this range, the question that goes out up to what, 500,000.
Yeah. Yeah.
But then there are other supernovae which have been observed longer. There's a whole
So are
lot of
those like the
information
very
sitting
closest ones? Or, okay. Yeah,
So
yeah,
1979C was one of the shows. As you can see, this is like 40 years ago.
Right. No, that's a good point. That's a good point. So already it's
Yeah.
for sure to be a closer one.
Yeah, but there's a lot of information. The observations can provide a lot more information. So this model about the binary interaction
Yeah.
and the output coming out, I haven't looked into details of how exactly they did
Already
it,
about it. Yeah.
but it will be fun to, because if I imagine their scenario, I see a problem there.
Great. Let's talk about it.
Yes.
Okay. Let's regroup. Thank you all for the quick break, but maybe you have to know food in front of you. So questions for that fish.
Hi, Peter.
So based on your second point, when you say case closed, type 1As are double degenerates?
Yes, that is correct. So, absolutely clear, right? But we should keep observing. As I said, this puts limit only on 90% of them, but most of them, that means, are double degenerate. Yes.
I'd like to contest that.
Oh, okay.
Because first of all, the single degenerate doesn't necessarily mean that you have a giant donor. You can have a donor that is either more massive than the white dwarf, but it's still on the main sequence, or it can be a subgiant with a core mass of, say, 0.15 solar masses, 0.2 solar masses. And in those cases, the mass loss rate is indeed about 10 to the minus 7 solar masses per year. So that may be, if you're talking about the full range of single degenerate models, where the donor star will have been giving mass right up until the end, it's not clear that giants are the main mechanism. And in fact, there are papers that say they can't be more than a few percent of all of the single degenerates. So that's one point. Second point is that we don't really understand nuclear burning white dwarfs and what they look like, because in the cases where we're pretty sure we have nuclear burning white dwarfs in the Magellanic Clouds in our galaxy, where they do have these main sequence or subgiant donors, we don't know if they're going to be supernovae, but they're the same class of object. Yeah, well, that's what is thought, right?
Okay, yeah.
They're really poorly understood even still. But one of the really weird things that we don't understand about them is this, that they have very bright, they're very bright and soft X-rays, and that means essentially they're extreme UV sources. They ionize the region around them, and if there's gas that has typical densities of about, say, 1 per centimeter cubed, you would have these incredible ionization nebulae extending out to something like 10 parsecs. And for the dozen or so that have been checked, only one of them has this. And what that seems to mean is that this region around them material has been blown out of there from something early. So that would kind of destroy the signature that you're looking for, even in a large fraction of potential single degenerates.
That's right.
And then the third point is that, well, actually 4 points. Third point is that if the white dwarf has spun up significantly during mass transfer from either an unevolved star or a giant, it needs to spin down before explosion. So especially if you had a giant, and if that giant had something like 10 to the 6 years more of mass transfer, but the spin down time is 10 to the 7 years, the giant won't be there, and it won't even necessarily have a lot of mass around it by the time the explosion takes place. These are the so-called spin-up, spin-down models, and that you can't rule out this way.
Absolutely. Yes.
And finally,
Yes.
double degenerates. Double degenerates, before they become double degenerates, it has to be a giant with a highly evolved core and a white dwarf. Because the only way you can get two white dwarfs that are both pretty massive and that are going to give you a supernova when they come together is if in the last phase, before they came together, one of them was the core of a pretty well-evolved giant. That pretty well-evolved giant had to fill its Rocheleau, produce the common envelope, the two things came together. The common envelope is still there for a while. So in cases where you have a prompt merger, and there have been some 1As where there's evidence of material in the vicinity, where you have a prompt merger, it could easily be a double degenerate, but have a lot of material around it. So the point I'm making is that the picture is much more complicated, and therefore, I know people like to have definite results, and that's it's true that you could make it double degenerates. That would be a beautiful result because it would really be definitive. But I guess the point I'm trying to make is that there are so many possibilities. It's such a rich field that I think we still have a lot to do before we can genuinely get down to that very strong statement.
Absolutely. I think your point is very much valid. And before giving the detailed answer, I would say we are being very precise and accurate in saying that it's the white dwarf red giant association that we are ruling out. That's one thing. Second thing is that this applies to the supernova that we have seen, which is not the type 1A supernova in the entire universe. It's only like within 100 to 200 megaparsec. That's how far radio observations can go. So this particular conclusion associates to that, but I'm an observer, and I strongly believe in observations than theories. So it's good to come up with different scenarios to get rid of this. But it's a fact that is hard to deny within that limit.
No, I think this is great. It's a great specific result, but it doesn't tell you that double degenerates are the main pathway, and it doesn't tell you about wide ranges of single degenerates that people were studying long. The theory
Sure.
didn't come afterwards and say, how do we get around this?
Sure.
The theory was there, and then observations tested. So you're testing one piece of the parameter space.
That's right. And the other thing I should mention here is that, now this is not from radio, but from optical observations. Like if you have a companion sitting next to this type 1 supernova, the shock wave will interact with that, and you should be able to see some signature in optical at UV. There was a claim a couple years ago that such a signature has been found. There was a paper in Nature. Nothing more has happened since then, but it's possible. So at least in that one case, if you believe that result, it's possible that there is a companion. So that scenario is not ruled out entirely. All the scenarios that you said, I'm sure that there is a way to calculate what percentage of that contributes to this, and they all should sit together. So what I'm trying to say is that the radio observations point that this looks like very dominant process here within the local universe, and they must sit together with various theoretical scenarios that one can come up with. Right? So there may be 5 different scenarios in which we can make type 1As, but they should match to this number. We cannot deny this. 90% of the supernovae, we don't have any radio observations. We do not have any radio detections.
I very much believe in observations, and I've done some to try to pin these things down. And actually, this would have been what people like Mario Livio predicted ahead of time, because they said you can't really make too many type 1A supernovae this way,
Exactly.
even though they like single degenerates.
Yes.
So maybe time for 2 more questions.
I have only one question. So the plot right before this, I think you were showing the primaries and secondaries. Maybe.
Right, this one.
Yeah. I'm surprised that the secondaries have the same spectrum as the primaries.
Right, so what happens is this. There are various processes that have gone into calculation of this. The simplest is synchrotron emission, which is synchrotron self-absorbed, by the way. And then there is free absorption, because if you have extremely dense material, the emission gets absorbed. So that gives the steep rise. And the various things that you're mentioning are all hiding inside this, which is why they look similar.
Okay.
Yeah, but you're right. So a main difference here between the primaries and secondaries is that primaries can have their Lorentz factor all the way to 1, with lower injection energy. But the secondaries will always start with a specific number, which is a reflection of the fact that they come from ions, and which is about 100. So now that gives me an opportunity to show you another slide here. One before. Right, so how do I move this? Why is this not going? Right, so this is a proton distribution. What is plotted is gamma square versus n gamma versus gamma. And the blue lines are the electron distribution, secondary electrons.
Good. That's what I expected to look like.
Yes.
Good. I wasn't thinking about the free freedom.
Right. Why is this not moving? Right. So you can see that the blue curve here, it starts to peak at around 100, which is the signature of the secondary electron, the fact that they come from ions and not from any other acceleration process. But that is hiding in that free absorption. So, which is why they look similar.
Okay, thanks. Last slide.
You started out by telling us you were going to show us a photo album, but there's only one picture. In other words, you're always talking about one mass loss rate. Is there any way you can see what the history of the mass loss was? I mean, that's a real issue in these luminous stars. Does it come out smoothly? Does it come out in bursts? Does it stop for a couple of centuries? Or how does it all work?
That's a good question. So what I'm saying is that if you look at different supernovae, you will get a different picture. Okay?
Yeah, but it's always one number. You gave us one mass loss. Well, the number may change, but it's only one number per supernova.
No.
All right. Well, okay. Tell us.
So let's look at this particular light curve, supernova 14C. Now, if I estimate mass loss rate here, it's about 10 to the power minus 6 solar masses per year. If I estimate that number here, it's about 10 to the power minus 4, even higher than that. Okay, so the mass loss rate has changed over this time. This is the photo album I'm talking about.
Okay, you didn't, yeah, okay.
I didn't explicitly
come
mention
through.
that.
It didn't come through.
But that's a good
Okay,
question.
so what if you put time and mass loss rate? Do you have a figure like that?
I do have it, but not in this particular. I'll show you.
Okay.
That's a very good point. I'll show you.
So what's the characteristic? Does it go up and down? Does it continually increase?
Oh,
Does it
various things
continually
happen.
decrease?
Various things happen. So in this particular case, because the star had expulsion a couple centuries ago, you see this thing. If you have simple wind, it's all homogeneous, but still you can plot different supernovae. And what you see are some extremely important conclusions can be drawn from there. In many cases, what I see is that the mass loss rate, that is, there are limits by line-driven mass loss rate and various different.
Yeah.
Most of these supernovae tend to go either way beyond that or way below that. And it's extremely hard to see why that happens.
Okay, thank you.
But I'll show you those plots.
Okay.
Thank you.
Let's thank both our speakers again and thank you all for coming.